Alrighty, lads and ladies, welcome back. This is, of course, Calc 1 Honors, and today you may notice I'm coming to you from a different room. My wife, in her infinite wisdom, suggested that I move my office setup back here to the spare bedroom because we don't have anybody staying with us right now, and this way you hear less baby, you hear less dog, you hear less of the kind of noises that have been a little bit disruptive thus far. So I hope that this is a positive change for you guys. Yep, that's all. So we're going to continue. Oh, sorry, go ahead.
Did you grade the score?
No, I have not graded the tests yet. Still working on that. So you guys are one of 5 classes, all had tests last week, so I'm grinding it out as quickly as I can. My goal for you guys, I think, is to have them by Wednesday, right? You guys tested last Wednesday. So I'll do my best to have your tests ready in 2 days. Oh, not there yet. So I apologize. Oh, no apologies. So a week is the normal thing. But I know you want them back as quickly as possible, and I promise I'm working hard to get them back as quickly as possible. It just takes time. But we are going to pick up today where we left off last time. So last time we were talking about implicit differentiation, how to differentiate when you aren't necessarily solved for y, and recover y prime, or dy dx. We used implicit differentiation to find the derivatives of the inverse trig functions. That was very exciting. And today we're going to see how to use implicit differentiation to find the derivative of some other functions that are also defined as inverses, namely logarithms. So that's where we are going today. MAC 2311, the section is OH1, which means this is Calc 1 Honors. And today is the 4th of October, 2021. And as promised, today we're going to learn what's called logarithmic differentiation. And the section in your textbook, I think this is 3.6. Yeah, 3.6. They call it derivatives of logarithmic functions. We're going to go a little further than this. Now, this also means that we're starting to get a little bit close to the next student teaching thing. So I do want to take a quick look at that and just see which one is it. 2823 is this one. So where are we at? The next student teaching thing. Oh, and we still have someone who needs to send me this stuff. So William, if you're here, please, as soon as you can, I need this stuff from you. And Natasha, it looks like I still don't have an honors project topic. So if you've sent me these, then I missed them in the email. It's possible that you have sent them, but if you have not, which I believe is the case, please send these immediately. We do need this stuff, especially the honors project. But our next student teaching section is going to be, oh, we don't have anything up till 4.9. So there's still a couple up for grabs too, right? Like 4.1 on mins and maxes, that's still up for grabs. That's a nice section to student teach. So if William, you're interested in that, we are starting to get close to that. Now would be a good time to begin preparing if you wanted to grab that one. So yeah, logarithmic differentiation, which is section 3.6, we will be covering today. And then let's take a look at your syllabus also. So log derivatives, that's today. And then we'll be talking about related rates. This is a slightly tricky section. So this is kind of the next big stop for us. I may be able to introduce that a little bit today. Linear approximation, that's another section that is available for student teaching. So maybe take a look between 4.1 and 3.10 and see if you would like to teach either of those. But that's where we're headed. So let's do it. So we're going to talk about logarithmic differentiation, derivatives of log functions, and then we're going to introduce related rates. Which is section, I think, 3.9. So there are a few sections in there that we're jumping over. Those are application sections. We'll talk a little bit about applications in a few places. Related rates is all applications, but those other sections in there are not important. Oh, okay. Yeah, William, I'm so sorry if I missed that. The 4.1 stuff, I must have just not put it in the spreadsheet. So that's fine. Let's go ahead and make an arrangement where we can talk over your notes. So I'll just say that begin kind of preparing, right? Start reading the section, developing some notes, see what examples and theorems you want to cover, and then come by one of my office hours in the next week or so we can talk about those things together. And then we'll schedule a practice run so you can practice the lecture with me before actually having to deliver it. Exam grades. So my general rule for exams is 1 week from the day of the test. And you guys tested last Wednesday, at least the majority of you tested last Wednesday. So I'll have those back for you probably by Wednesday. That's my goal. All right. And while we're here, let me go ahead and you did send that to me. I'm so sorry. 4.1. I might have put it in the other one. This thing saves 2 copies. Oh, I bet maybe that's it. It's saved from the other one. Okay. So logarithmic differentiation. Logarithmic differentiation, we got to start out by learning how to differentiate logarithms. And then there's this really cool trick to differentiate big nasty expressions by first taking the log. I think you'll find that quite cute. It's actually really nice. But in order to do any of that, we need to know how to differentiate the log function. So let's do it. The trick is implicit differentiation. We use implicit differentiation. And I'm just going to start by looking at, suppose y is equal to the natural log of x. I want to find y prime, right? I'm trying to find the derivative of ln x. Obviously, I can't just dive in here and differentiate on both sides because I don't know how to differentiate ln x. It's the exact same problem that we had when we tried to differentiate the inverse sine or inverse tangent function. We don't really have anything that I can apply my rules to. Ln of x is not a product or a quotient or a sum or a difference or a power or anything like that that we know how to differentiate. It's its own thing. So we have to come at it indirectly. Implicitly. Here's the deal. Y is equal to ln x means the same thing as e to the y equals x. That's the definition of the logarithm. So we can differentiate this implicitly and then solve for y prime. So I apply the operator ddx to both sides. It's very similar to what we did with the inverse trig functions. The right-hand side, the derivative of x, ddx of x, is 1. On the left-hand side, the derivative ddx of e to the y is what? Well, this is where I'm going to use my implicit differentiation. Remember, it's like the chain rule. Y is just secretly a function of x. So when I differentiate e to the y, I'll get e to the y back. And then I multiply by the derivative of the inside. The derivative of y is y prime. And the thing I want is y prime, right? Y prime is the derivative of ln x because y is ln x. So I'm now going to solve this for y prime. Y prime, okay, it's 1 over e to the y. It's dividing both sides by e to the y. And then e to the y, if y is equal to the ln x, e to the y is x. So 1 over e to the y is 1 over x. And that's it. If y is equal to ln x, then y prime, the derivative of ln x, is 1 over x. So i.e., the derivative of the natural log of x is 1 over x. And this is something you need to tuck in your pocket, remember forever and ever, amen. The derivative of ln x is 1 over x, just like the derivative of sine is cosine, the derivative of secant is secant tangent. The derivative of ln x is 1 over x. You got to know it. You don't want to go through this every time. If you forget it, you could do this, right? It's not that much work, but you don't want to have to do that every time. It's a little bit clever, right? And we don't, well, it's nice to do clever things. It's not nice to have to redo clever things you've already done once. So please do remember. If I wanted to differentiate some other base logarithm, I could do it the same way. Or you can use the change of base formula. From your algebra classes. The change of base formula says, if you start with the log base b of x, you can rewrite that as any other base logarithm you want. You can write that as the log base c of x divided by the log base c of the old base. A special case of which, where you set c equal to the number e, is log base b of x is equal to the log base e of x, or ln of x, over the ln of that old base b, which is, and what I'm going to do here is I'm going to split this fraction up because the bottom is just a constant. If b is just a number, the base of the logarithm function you're starting with, then the ln of b is just a number. So I can write this as 1 over the ln of b times the ln of x. All right, that's just how fractions work, right? A over b is the same as 1 over b times a. So the derivative of ln x is 1 over x. That means the derivative of some other base logarithm, the base b log of x, by the change of base formula is the derivative of 1 over ln b times ln x. Pop quiz, do I need the product rule? Do I need the quotient rule? Do I need any of that stuff to do this? Looks like a product, doesn't it? One function times another function, product rule? Yes, no? What do we think?
I think it's product rule and the chain rule.
It's a reasonable statement, right? And if this thing right here was a variable, you'd be right. But remember what we said a minute ago, if b is a constant, then the natural log of b is also a constant. So this whole thing right here, 1 over the natural log of b, is a constant multiple. So the only rule we really need here is the constant multiple rule, which says constant multiples pop out of derivatives. So this would be 1 over ln of b times d dx of ln x. So we're very lucky. We're very lucky in this that we don't need any of those rules. And this is because, I'll annotate here a little bit. Finally found all my colors. Because 1 over the natural log of b is a constant. We're using the constant multiple rule. All right, so 1 over the ln b, this is like 5. So if you want to differentiate 5 times ln x, you just pop out the 5 and differentiate ln x. Now, is it always going to be 5? No, but it is always going to be a constant. So we get 1 over the ln of b times the derivative of ln x, which we just found is 1 over
1 over x.
Yes, exactly. Beautiful. All right. So the derivative of the base 2 logarithm, for example, would be 1 over the natural log of 2 times 1 over x. The derivative of the base pi logarithm would be 1 over the natural log of pi times 1 over x. That's it. Nothing too crazy. The truth is, you're like never going to see this. It's very, very rare that you differentiate any logarithm other than the natural log. The only way it shows up is if somebody's making a problem and wants to like throw you a weird one. They don't show up in a lot of places. If you're a computer engineer, I take that back a little bit, right? So if you're a computer engineer, like specifically computer hardware engineer, then you deal with the binary logarithm, the base 2 logarithm somewhat often. So you may end up differentiating the base 2 log, but it's not super common. The good news is that either way, all you need is the change of base formula and the derivative of the natural log. So it's not bad. Okay. Let's see. So what sort of examples could we look at here? Tangent line stuff is always good. Let's find the equation of the tangent line to f of x equals the ln of x at x equals e. Just because I care a lot about this, I want you to draw the graph of the natural log function. I know that it's possible to get through pre-calculus without remembering what this graph looks like, and I think that's a goddamn tragedy. So here is what the graph of the natural log function looks like. You have a vertical asymptote at 0, crosses the x-axis right here at 1, and over here at E is the point E comma 1. So the y value there is 1. And the tangent line that I'm looking for there is this one, right? So you got to know what the graph of the natural log looks like. And I don't say that to like be mean to you. I know that it's not always the case that we remember that. And I want you to please remember it. Okay, so let's find the equation of this blue tangent line. We know that the slope of the tangent line will come from the derivative. I need a point and a slope. All right, I want to find the equation of any line. I need a point and a slope. The point is the point on the graph here, which is e comma 1. How do I know it's 1? Because the natural log of e is 1. And this, again, is something you need to know. We need to know how to work with logarithms. So that would be one of those basic things. The slope is going to come from f primed of 1.
Sorry, I cannot understand why the point e comma 1. Okay, I see. Thanks.
Yeah, okay, yeah, nothing crazy, right? It's just that ln of 1, right? F of 1 is the f of e. F of e is the ln of e. And the natural log of e would be the number to which you raise the base to get the inside. The number to which you raise e in order to get e is 1. So that's where the 1 is coming from. All right, the slope is going to be f prime of, I'm so sorry. I keep saying the word 1 over and over again, so I'm like ruining it in my brain. The slope is f prime of e, right? It's the derivative of the black function at this x value. F prime of e, sorry. So let's find that. I know that f of x is the ln of x. So f primed of x is 1 over x. So f primed of e is 1 over e. Yeah, good catch on that, Tully. I'm sorry. So the slope is 1 over e. The point is e comma 1. So the tangent line is y minus 1 equals 1 over e times x minus e. And that's job done. Thank you. Okay. What other fun stuff can we do? This is before we dive into the logarithmic differentiation. Let's find some horizontal tangent lines. Let me see. Your book should have some examples here. So I don't want to risk messing things up. Bad numbers. Do all that stuff later. Logarithmic differentiation is cool. Power. Okay, we'll get to that. No horizontal tangent questions. Give me 1 second. I have a good example in mind that I'd like to run through, but I need to make sure that I'm. Yeah, we can do this, right? Yeah, pretty sure we can. Yeah, okay, I got this. So another fun thing to do is to find the location of any horizontal tangent lines. So let's find any points x comma y where the function f of x equals x ln x has horizontal tangents. We had a question like this on our first test. What do we need to do? How do we find the location of horizontal tangent lines?
Prime is equal to 0.
Yeah, exactly. We need to solve the equation f prime equals 0. All right, I'm going to try to find all the x values where the derivative is equal to 0, because the derivative is the slope of the tangent line, and I'm looking for horizontal tangent lines. Those are lines where the slope is 0. All right. So in order to solve that equation, I need to know what f prime of x is. Well, whatever it is, it's definitely d dx of x ln x. Right? And now this does require the product rule, right? Because this is not a constant. X is a variable, it changes. So we'll apply the product rule. And get, you can write it out in that prime notation, it'd be x prime times the ln of x plus x times the ln of x primed. X primed is 1, so this is just ln x plus x times the derivative of ln x is 1 over x. So the derivative of this function is ln of x plus 1. And when I cancel these to call that 1, I'm assuming x is not equal to 0, but we're assuming that anyway because the natural log of 0 is undefined. So f prime of x is equal to 0 if and only if 0 is equal to the ln of x plus 1. And I can subtract 1 from both sides. I get negative 1 is equal to the ln of x. Now, how do you solve an equation like this, where the variable is stuck inside a logarithm? Who remembers this from the skills test?
Both sides e to the
Yes.
raise up.
Yes, the word I like to use is exponentiate. We stick both sides in the power of e. This step here, this is called exponentiating. Whatever the base of that logarithm is, in this case, base e, because e to the ln of x is what?
X.
Just x. Very good. Okay. So we have victory. F prime is equal to 0 if and only if x is equal to e to the negative 1, or 1 over e. Therefore, f of x has horizontal tangents when x is equal to e to the negative first, which most people would write as 1 over e. And the point, remember they asked for points, x comma y, on the graph is 1 over e comma what? Well, I have to find f of 1 over e. And f of 1 over e, remember f of x is x ln x. So f of 1 over e is 1 over e times the ln of 1 over e. 1 over e is just 1 over e. What is the natural log of 1 over e?
-1.
Very good. Very, very good. Times -1. So this is -1 over e. So we plug that guy up in here, and our point. One over e, comma, -1 over e. Okay. Just some fun stuff that you can do with these. So we know how to take the derivative of a log function now. That's good. And we can do all the stuff with that that we would do with any other function. We can find tangent lines, we can find the location of horizontal tangents, instantaneous rates of change. If this was a velocity or acceleration function, we can do that. The place I want to go from here, though, is much cooler. The place I want to go from here is where we're going to use logarithms to make nasty derivative problems unnasty. So let me show you an example of a nasty derivative problem. Here's something we don't want to do. The following is nasty. Example, find y prime where y is equal to, let's fuck our day up pretty bad here. How about x times e to the x times x squared plus 1 to the 3/2 all divided by the square root of 1 minus 2x. How badly do you not want to do this? Let me make it worse. Times the tangent of it. Let's get some trig in there. I really don't want to do this. Like, really don't want to do this. Look, it's a big quotient, so we need a quotient rule. The top is a big product, not one product, but two products, right? 3 terms total. So you need 2 product rules just to differentiate the top. And then within that, you'd have a chain rule here. And the bottom is also a product. And within that, you would have a chain rule with this. So if you wanted to do this the normal way, using the quotient rule, product rule, and chain rules, you would be here all day. And what's worse, probably make a mistake somewhere, because there's so much shit to do. This would normally require lots of quotient, product, and chain rule. Even I would make a mistake. Even I would fuck this up. I promise you I would make a mistake somewhere. Maybe not every time I try it, but at least once. You know, if you give me like 3 shots at this, probably I make a mistake at least once or twice. And most Calc 1 students would have a very hard time even beginning. It's nasty, 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 nasty. Now, do you remember back in your pre-calculus classes or your high school algebra classes, wherever, when you were made to over and over again, you were told that, you know, here's some logarithm expression, expand it as much as possible. You ever wonder why? This is why. Instead of attacking this directly, I'm going to take the natural log on both sides, and then I'm going to expand and differentiate each one of those pieces. Because the logarithm turns multiplication into addition and powers into constant multiples and division into subtraction, we can clean this up a lot by taking the natural log on both sides. How does that look? Well, it looks like this. On the left-hand side, I'll have the ln of y. And to differentiate this, I will need implicit differentiation. On the right-hand side, at first it looks like this makes things worse. I'm shoving everything inside of a natural log. Well, doesn't that just give us more work? No. Because I can use properties of logarithms to expand this. I'm going to expand using the log properties, then differentiate. What are those log properties? Well, just in case you forget, I'll write it for the ln. The ln of a product is the ln of the first thing plus the ln of the second thing. The ln of a quotient is the ln of the top minus the ln of the bottom. And the ln of a power is that power times the ln of the base. These are the log properties we will use to expand that statement. The first thing I'm going to do is take this quotient and split it up. So this will be the ln of the top minus the ln of the bottom. And now each one of those things, I've got a bunch of stuff multiplied inside. So I can use this first rule to split up both of these log expressions as a sum of simpler log expressions. From this first guy, I get ln x plus ln e to the x plus ln x squared plus 1 to the 3/2. Now this minus right here is going to go to both pieces that I get when I expand this guy. I have to distribute that negative. So this will be minus the ln of the square root of 1 minus 2x minus the ln of tangent x. So here I've done a pretty good job of expanding, but there's still more I can do. This is a power. This is a power. This is a power. So I can use my third rule to expand further. Altogether, I get the ln of x plus the ln of e to the x is just x plus the ln of some shit raised to the 3/2 power is
3/2 power multiple,
very good.
not greater than x squared plus 1.
Perfect. Right, this power comes down. The square root is also a power. It's a 1/2 power. So this is 1/2 times the ln of 1 minus 2x, and the natural log of tangent stays the same. Now I have expanded everything. And each one of these pieces is easy to differentiate. Some of them little chain rule, little chain rule, little chain rule. Some of them just straight up, don't even have to worry about chain rule. So here's what we have, right? The left-hand side is still the natural log of y. So now I can differentiate on both sides. I'm differentiating implicitly with respect to x. On both sides. Okay. I'll just write it as d dx ln y on the left. And on the right-hand side, I'm going to go ahead and start taking derivatives. All right, so I have d dx of all this stuff. The d dx of ln x itself is 1 over x. d dx of x is 1 plus d dx of ln x squared plus 1. This requires the chain rule. So I differentiate the outer function, leaving the inside alone. That's going to give me 1 over x squared plus 1. And then we have to multiply by the derivative of the inside. Maybe I'll write that in the prime notation for now. And the other pieces here also require the chain rule. This next piece is going to be minus 1/2 times the derivative of the outer function, leaving the inside as 1 minus 2x. That's going to be 1 over 1 minus 2x times the derivative of 1 minus 2x. And finally, this last guy, ln of tangent, we'll get 1 over tangent x, differentiating the outside, leaving the inside alone, times the derivative of tangent x. Okay, so take a second, look at these guys and make sure you're actually comfortable with these little derivatives here. Each one of these is something new, right? Something we haven't seen yet. But it really is just the chain rule. The derivative of the natural log of x is 1 over x. So the derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1. This is a chain rule. This is a chain rule. This is a chain rule. I'm sorry, Yiping, what were you going to say?
Oh, I was just wondering for the third term, why the constant 3/2 isn't included
Yes,
as multiplied by that?
Nope, you're right. You're right. I lost the 3/2. I'm sorry.
Okay, thank you.
You're absolutely correct. I messed it up even this way. Well, these are tricky, right? This was a nasty problem. Okay, other questions or comments? Are we all comfortable with where, for example, this derivative is coming from? On the left-hand side, I haven't taken this derivative yet, right? ddx of ln y would be 1 over y times y prime. And now I'll come through the right-hand side and start cleaning things up. I've got 1 over x plus 1 plus 3 halves times 1 over x squared plus 1 times the derivative of x squared plus 1. Well, the derivative of x squared plus 1 is 2x. And x squared plus 1 still chilling downstairs. And the 3 halves is there. I'll write that as 3 upstairs, 2 downstairs. Then I've got minus this guy. So the derivative of 1 minus 2x is negative 2. Downstairs, I have the 2 from the 1/2 and 1 minus 2x still. The derivative of tangent x is secant squared. So this last piece is minus secant squared x over tangent x. And there is some cleaning up that can be done. The 2's cancel here, the 2's cancel here. Secant squared over tangent, this can also be cleaned up. That's 1 over cosine divided by sine over cosine. So you flip the sine over cosine to cosine over sine times 1 over cos squared. You get sine over, is that sine over cosine, yeah? Yeah, oh, that's nice. Maybe one more line. I have 1 over y times y prime equals 1 over x plus 1 plus x over x squared plus 1. Minus minus here will make plus. We canceled the 2, but that negative is still there. Plus 1 over 1 minus 2x. Minus, what did we say this is? Secant squared is 1 over cos squared. And we're multiplying by cosine over sine. So one of the cosines will cancel. Let me write this out. This is 1 over cos squared x times cos x over sine x. You can cancel one of the cosines. Ooh, and we get not cos over sine, we get 1 over cos x sine x.
Okay, nothing.
Okay.
Yes, that's good.
All right. Now, the last thing we would do here, we got to multiply both sides by y, because I want y prime. So y prime is y times all of this. And if you want an explicit expression for the derivative instead of an implicit expression, if you want to get rid of this y, you would plug back in. What was y? Y was this thing. But you don't have to. This is an implicit expression. We have done it. We have found y prime. And like I said, if you want an explicit expression, just plug back in for y here. You could have a common denominator among all of these things if you wanted and rewrite it as a single fraction, again, if you want. Did I lose a 3? Yes, I did. I'm sorry. For some reason, my brain just doesn't want to see that 3 halves. Yes, very good. Thank you. This 3 did not go away. This 3 right here, still here. The 2's go, the 3 didn't. So this 3x upstairs here, 3x upstairs here. So this takes a problem that is almost completely intractable, one where we really wouldn't have a hope of finding y prime using the regular tools, at least not without spending all day on it. And it allows us to attack, which is pretty cool. Now, are you ever going to be asked to differentiate something this heinous? Nah. But will you be asked to differentiate stuff like e to the x over the square root of 1 minus 2x? Sure. And that would be a good candidate. Or x squared plus 1 to the 3 halves over tangent x? Sure. And that would be a good candidate. So if you want to differentiate a big quotient or a big product, and you don't want to use the quotient or product rules, then take the natural log on both sides first, and then differentiate implicitly on both sides. This whole procedure here is called logarithmic differentiation. And it can save us a lot of work, because the logarithm takes algebra operations that don't play nice with the derivative, like multiplication and division and powers, and turns them into things that do play nice with the derivative, like addition, subtraction, and constant multiplication. But it doesn't stop here. There's more that we can do with logarithmic differentiation that we just couldn't do before. So this is something that we could have done before, but it would have been unpleasant. Something that we could not have hoped to do before, like literally not possible before, would be this. I can say find y prime, where y is x to the x. If the power here was constant, then I could use the power rule. If the base here was constant, then I could treat this as an exponential, right? Like 2 to the x or 5 to the x. We know how to differentiate those. But here, both the power and the base are variable. None of our rules apply to this. None of our differentiation rules apply here, because the power and the base are both variables. Neither of them are constant. But logarithmic differentiation will save the day. You see, I start with y equals x to the x, and I take the ln of both sides. And then the ln of x to the x is x times the ln of x, right? That's that third property of logarithms, that powers inside come down out front. So if I apply d dx to both sides here, I will be able to recover y prime.
Excuse me, I have a question. When do I use the logarithm property? When do I use only logarithm both sides? Because I hear the x to x, I can treat it logarithm x minus logarithm x, I think.
Not quite. So if this was the ln of x over x, then I could treat that as ln x minus ln x. But because this is a power, so the rule I'm using here.
So if the power is constant, I can use the the base the same and the logarithm minus logarithm x divided by logarithm x is equal to logarithm x. If the power is constant, I can use that way. But here the best way is logarithm both sides and get the power out of the parentheses.
Yeah, so if this was a constant, then we wouldn't need any of this. We could just use our power rule, right? Like bring the power down, reduce the power by 1. If this was like x squared or x cubed or even x to the pi, as long as the power is constant, we already knew how to differentiate that. That's just the regular power rule. And if the base was a constant, like 2 to the x or 5 to the x or e to the x, those are regular exponential functions. We know how to differentiate those. So the hint here to use logarithmic differentiation, the hint that tells us to take ln of both sides, is that both the base and the power are variables. If both of the base and the power are non-constant, then this is the only way to proceed.
Thank you.
Yeah, of course. So applying d dx to both sides, the left-hand side will become 1 over y times y prime. And the right-hand side requires a little product rule. That's going to be the derivative of x, which is 1 times ln of x. This is the function we differentiated earlier, right? Plus x times the derivative of ln x, which is 1 over x. And then multiplying both sides by y, we get y prime is equal to y times 1 times ln x is just ln x plus x times 1 over x is 1. And again, this is an implicit expression, but if I wanted an explicit expression, I just plug this in. So y prime would be x to the x times ln x plus 1. And this is a derivative that we could not have found otherwise, which is pretty cool if you ask me. And it's not really a new rule, it's kind of a trick. But it's a trick that opens up new stuff. All right. Any questions on how I get this answer here? So this would be my answer. This is y prime.
This is explicit.
Yeah, exactly. So this first version here, this would be implicit. And this version here would be explicit. And we like explicit wherever possible. If it's not horrible to write down the explicit derivative, I would generally prefer that because it's easier to work with. All right, silly question. X to the x. What do you think this graph looks like? Do you think this grows very fast or very slow? Some values here would be like 1 to the 1, 2 to the 2, 3 to the 3, 4 to the 4, 5 to the 5, 6 to the 6, 7 to the 7. Yeah, it grows really fast. Let me show you some comparisons. It looks a little bit like that guy. So there's problems with complex numbers, right? if Desmos, the reason it's doing weird stuff over here is because it's trying to plug in negative values for X, which is no bueno for this guy. But yeah, look at that. Really steep, right? Like straight up. Comparing to some of our other favorite functions, here's e to the x, and you see that the red quickly outpaces the green. Let me rescale my y-axis a little. See, the red grows way, way faster than e to the x. And let's compare it to like x squared. Not even close, right? X squared is like a baby compared to these things. So the purple is the slowest growing here, then the green. The green grows pretty fast, but look how much steeper the red is. It's going like straight up. And we usually think of e to the x as going like straight up, but the red's even faster. There's really not much that compares to this. Maybe you guys don't know this one yet, x factorial. But even that, if you're familiar with the factorial function, even the black function here is outpaced by the red function, and it's really not close. So just comparing to a few other kind of well-known functions, let me restrict this to greater than 0. X squared, very, very slow compared to e to the x. And even e to the x is very, very slow compared to x to the x. So this is an incredibly fast growing function. Okay, we're doing on time, 12:08. We got a few minutes left. Let me take a look at your textbook and see if there's another problem or two we want to solve in here. Differentiate these. Oh yeah, I've got a little shortcut I can show you for something to differentiate, find the domain. Yeah, let's look at that. All right. So a useful shortcut. It's really just the chain rule, but if u equals u of x is a function of x, then the derivative d dx of the natural log of u is u primed over u. All right, we've been writing it as like 1 over the inside times the derivative of the inside. But that's the same as the derivative of the inside over the inside. And these things actually have a special name. This would be called the logarithmic derivative of u. You won't need that terminology, but if you decide to ever study analytic number theory, you'll see it. Okay, let's look at 1 or 2 more quick examples here. So if I want to calculate d d theta of the ln of sine theta, here my u is like sine theta. So this would be the derivative of sine theta divided by sine theta itself. And the derivative of sine is cosine. So this would be cos theta over sine theta, or cotangent theta. Just a silly shortcut. One last thing, and then I'll let you go. One last problem here. I only do this because there's a terrible joke that goes along with it. So in my particular field of mathematics, which is analytic number theory, there's a type of function that shows up a lot, which are like logarithms of logarithms of logarithms of logarithms, where you repeatedly compose a logarithm. So the joke is, what is the sound made by a drowning analytic number theorist? Log, 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 log. That's it. It's a bad joke. It's a bad joke, and I'm sorry. We find f prime of x, where f of x is the ln of the ln of x. It's number theorists would call this the log of x. All right. F prime of x is what you get by differentiating f of x. So it's d dx of ln of x. And then we can kind of use that trick I just showed you, right? This is a repeated chain rule thing. The outermost function is here, and then the next level in is an ln of x. So this would be ln of x primed divided by ln of x, right? So I'm thinking, here's my outer function, here's my inner function. It's 1 over the inside times the derivative of the inside, or u primed over u. Here, this piece is playing the role of u. And the derivative of ln x, the thing upstairs, is 1 over x. So this is 1 over x divided by ln x, which is, you simplify the fractions, this is 1 over x times the ln of x, which is another kind of important function from number theory. If you take Calc 2 with me, I'll show you some cool stuff with these. Okay, I think that's all we have time for today. You guys now know how to differentiate logarithmically and take derivatives of all sorts of gnarly log functions. Sort of the toughest thing in here is this stuff, right? Where you're differentiating one of those functions where the base is variable and the power is variable. And I'll put a few of these into your homework. You do want to practice those. I think that's about everything that you could need. So I'll leave it here for the day. William, when we have some time in the next few days, just one of those office hours, we can drop by, we can chat a little bit and come up with a plan. And then we'll need to do one more meeting before we get to 4.1, where we can do like a practice run for your student teaching thing. What else? Tests will be back on Wednesday. That's the goal. And yeah, I think that's the game, guys. So please watch for that new homework. I'm going to go open that up for you right now. It will have plenty of logarithmic differentiation on there. And I will see you next time.
We have office hour today.
Yes. Yep. Normal office hours today, 1 to 2.
Excuse me, could you help me grade my score first? Because I have some questions confused. I want to know them.
I would like to, but I have actually other whole classes that tested before you guys. So when I get to your class, I can make a point of doing yours first. But I've got 2 or 3 other classes that I need to grade before I get to this class at all. So it's still going to be a little bit, but Wednesday, I'll try to have it for you by Wednesday. Okay.
Thank you.
All right. Take care.